Good morning, everyone. Am I audible? Hello? Okay, I'm sorry. I was okay. Okay, now it's okay. I thought it was unmuted. Okay, whatever it is. So, we have. I was talking. That means you have not heard anything, maybe. So, I was telling you about the plastic analysis. We are trying to. We are. We will be talking about the plastic analysis. This is the chapter I am going to take for you in analysis of structure and what is your basically analysis. This one, plastic analysis. This is defined as the analysis in which the criterion for the designer structure is the ultimate load. Okay, so basically we are telling that it is an inelastic analysis of the material which is to be studied beyond our elastic limit, which you can observe in your stress strain diagram. Okay, so this is your stress strain diagram. If we check in the stress strain diagram what is happening, if we check in the stress strain diagram, we have in some, this is your elastic zone, this one till here, from here to here is your elastic zone. This is a straight line, you all know already this thing, the stress strain diagram. Okay, and beyond this, after this elastic limit, when we have, this is your elastic limit, it's difficult to write like this, whatever. So it is elastic, and this side we have the plastic limit. Plastic limit, we know what is our elastic limit, you already know, because here in this portion we know what, if we apply a force or give some loading there and release the load, it will come, the material is going to come back to its original shape back. That's why it is elastic. But in inelastic plastic method, what happens, it doesn't come back to its original shape. And why is it actually so important to know this plastic analysis, why we are doing that? Because we know that in steel structure what happens, design is mainly steel structure design. In the steel structure design, what we know, main analysis of how much movement can a structure carry is done by the plastic analysis. Okay, that means the maximum load which your structure can take is depending on the plastic analysis, that is done by the plastic analysis. Okay, that's why it is important that we should know the plastic, we should do the plastic analysis. Suppose in a steel frame, the maximum moment carrying capacity by the beams or frames etc can be done only by plastic analysis. Okay, because in steel we know it has the ultimate, it can yield. Okay, in this thing, your steel structures. Okay, also if I stay you plastic analysis. Okay, there will be, we'll talk about the shape factors basically. Why? Because you will be asked to find out for different structures, steel structures, like it can be your square, it can be for square structure or rectangular structure, then for your circular you can find, and also for triangles you can find. Okay, so there will be triangles are also there where you have to find out the shape factors. Okay, so how good triangle. Yeah, it is a triangle. Okay, so triangle. Then we have the diamond. So also we will have some. Okay. So different types of shape factors. Also, we are going to find out the shape factors. Okay. Why? Because actually the ultimate load which is found, it is found from the strength of the steel in plastic range. Okay. Okay, we're not able to. Okay. Okay. Why we are doing passive analysis, because it is quite rapid and also has rational approach for analysis of structure. It controls the because it will also control the economy regarding the weight of the steel. Since the sections, these kind of sections required by this method are smaller than those required by the method of elastic analysis. Okay, plastic analysis. This kind of plastic analysis would also has its application in the analysis and design of intermediate structures like the frames. You can see the beams, plastic beams, the steel beams, etc. Basics of your plastic analysis is what? If I just can simply type here for you. Plastic analysis, if I see you, basics is what, basics of the plastic analysis is usually based on the idealization of stress strain curve, perfectly CTLY, perfectly plastic. Okay, so we have here this thing. The basic principle, if you see, is this. Okay, in plastic analysis, here we do what, here we assume, since I don't have the notes, I'm just simply typing here. I'm not ready with notes. I don't have my notes, or I got today that to teach you this plastic analysis. So I'm just typing here, okay, whatever I'm telling, because I don't have the perfect notes for you all. I have not prepared anything for your notes. I don't have anything. So here in this plastic analysis, basically what we are doing here, we are going to here we assume the width thickness ratio plate elements. Oh, where am I going? Assume the, okay, these things you remove these things. Okay. So plastic analysis is usually based on the idealization of stress strain curve as perfectly plastic. And here what we do, here we assume this width. Here we assume the width to thickness ratio of plate element is small, so the local buckling is not occurring. So the local buckling does not occur. Okay. Here in this analysis, we will assume that the width and the thickness ratio of the plate element is small. Why? Because so that this will not give the local buckling, so that there is no local buckling occurring. Okay, it's occurring here. Actually, we are. That means if I say you broadly speaking, if I say you, then that means the section SEC and the section will be declared as as perfectly plastic. Okay, perfectly plastic. So these were actually principle. These are the basic principles of your plastic analysis, where we know what that our plastic analysis is usually based on this idealization of stress strain curve. Here, this one. Okay, the stress strain curve as plastic, perfectly plastic, we are assuming this, and also in this analysis, it is assumed that the width, this one, the width to the thickness ratio of the plate element is small, so that there is no local buckling. That is, the local buckling is not occurring here. Okay, and also the section with so why, because of the section declared is perfectly plastic. So we will keep these assumptions in mind so that it can be said that this action will reach its plastic movement capacity, and after that will be subjected to considerable movement at applied moments. Okay. Okay, let me write this for you. Keeping in mind, if we keep keeping in mind these assumptions, it can be said that the section will reach its movement plastic movement capacity to considerable movement at applied moments. Okay. Okay. I think I have to remove so because this annotation, so this will get removed now. I'm not having. Okay. Okay. So I think I have to just. Now, this was the actually the general basics of your plastic analysis, and also now if we talk about the principles of plastic analysis, um, I think I have to remove this all. Note down these things because I don't have any extra notes for this. Now, if we talk about principles of plastic analysis, principles of plastic analysis. Okay, if I talk about the principles of plastic analysis, there are, okay, there are following conditions for plastic analysis. Okay, so what are they? First of all, if we talk about this mechanism condition, that means what in this mechanism condition, when the ultimate load is reached, collapse of the, it will collapse mechanically. Okay, so you can write here like when the ultimate load is reached, collapse mechanism usually formed. Okay, these are the conditions for plastic analysis. First is a mechanism condition where when the ultimate load is reached, collapse will take place mechanically, and that's why this is formed. Then number two, if we talk, that is the equilibrium condition. EQUIL equilibrium condition. So if we talk about the equilibrium condition, there we will have all this fx summation. I cannot show you the summation of fx, fy, then again movements, all this will be 0. Okay, and then we have the, how I'll show you the summation Summation symbol is not here. Summation of, let me write, summation of x equal to 0. Then we have summation of y equal to, all these forces are 0. We'll consider this, and then summation of moments equal to 0. Okay, now the third condition, if we talk, the third condition is your plastic moment condition. Okay, so that is PLASTIC, plastic condition moment. Oh, sorry, this is plastic moment condition. Okay, so these are the principles of plastic analysis. First one was your mechanism condition, second is your equilibrium condition, then next is the plastic moment condition. Here actually what we are doing here in the plastic moment condition, here the bending moment at any section, the bending moment in any section, here the bending moment in any section in the structure should be CT, or structure should not be more than the full, plastic moment. Okay, which means that the moment at which plastic hinge form and structure moves to failure. Sorry. Okay. My voice is low or what? Okay. So these are the principles of plastic analysis, where we have, there are following conditions for the plastic analysis, where we have this. Okay, the plastic moment condition is what? The bending moment in any section in the structure should not be more than the full plastic moment. That means where moment at which plastic hinges form and also the structures move towards failure, that is your plastic moment condition. Okay, which must be followed. Now, here, if we talk about plastic moment, when we are talking about this plastic moment, when we are talking about this plastic moment, there comes a term, I think you all know, that is the shape factor. Okay, for calculation of this plastic moment, shape factor, there is a term which is your shape factor. Okay, and that has its own importance. Okay, now when you have this shape factor can be defined, now we can talk about the shape factor. Okay, like for plastic moment, what is the plastic moment? I think you all know, like if we consider the case of a simply supported beam, um, okay, it takes time to show in this way, draw and show. So I'll just simply explain. Like if we consider the case of a when you consider the case of a simply supported beam, what happens there when the load is gradually applied? When your load is gradually applied, what happens? Your bending moment and stresses increases, right? When you have a simply supported this thing, when you have, Well, when you have this simply supported beam, what happens? When you apply a load there, when you apply a load here, when you apply a load here, it will start the bending moments and the stresses will also be increasing here. Okay, that means if this load here, if this load, uh, if as this load gets increased, the stresses and fiber also this thing of the beam reach to the yield stress. Okay, that means if we consider a simply supported, this simply supported beam, when the load is gradually applied on it, bending moment and this, we know that the bending moment and the stresses are going to increase. Now, as the load is increased, the stresses in these fibers of beam will reach to its yield stress, right? As the load gets increased, what happens? The fibers inside this beam reach to its yield stress. At this stage, now what happens? The moment which has converted the stresses into the yield stress is said to be a plastic moment. Okay. When your this load is increasing, what happens? Your fibers of this beam reach to the yield stress, and at this stage, what happens? The moment which has converted the all the stresses into a yield stress, that is said to be as a plastic moment. Okay, that means at this moment where you have a plastic moment, that means your stresses are converted into yield stresses. That then what happens? At this stage, the beam member cannot take up any additional moment but may maintain this moment for some amount of rotation and will act as a plastic hinge. That means what? Hinge means having no capacity to resist the moment. Okay, understood? That means when this fibers, when you have this plastic moment here, plastic moment, when it is said to be a plastic moment, when it is said to be a plastic moment, when your stresses are converted into yield stress, yes or no? So it is at that time what happens? Your beam cannot take up any kind of more moments, any additional moment this beam cannot take now. Okay, but this moment will maintain. Okay, but this may maintain this moment for some amount of rotation and acts, this will act as a plastic hinge. Okay, plastic hinge means what? Where hinge means having no capacity to resist this moment, that will this plastic hinge will behave like an ordinary hinge, which will allow free rotation about itself. Okay, so for knowing now this plastic moment, we have to know shape factors. That term, because it is related to that from the shape factors. Why? Because your shape factor, what is your shape factor? Your shape factor is plastic moment divided by your elastic section modulus. Okay, what is your shape factor? Your shape factor can be defined as the ratio of the plastic moment to yield moment. This one, elastic section modulus, that means the yield moment is said to be as the shape factor. Okay, this is your shape factor. This shape factor will also depend on the cross section. Like for rectangular, like in the at the very beginning, I told you about the rectangular, then circular, triangular. This kind of different shapes will be there. So if we can take an example of shape factor like rectangle, etc. Okay, so shape factor is this, that means your S suffix F, we can write it to be Z1 by Z2. Okay, where we have how much? Where your Z1 equal to how much? Capital A by 2 given by your Z1, which is your plastic modulus, right? So your plastic modulus is given by A by 2 into your Y1 plus your Y2. That is plus Y2. Okay. So we have this. Z1 is your plastic moment, and that moment is Z1 is given by A by area, A by 2, Y1 plus Y2. And we have also what? Z 2. Z2 you can say this you can say to be ZP, that means the plastic moment and section modulus. And here we have Z2. Z2 is what? The elastic modulus here, elastic section modulus. So Z2 is given by here, we know the elastic section modulus. Okay, it is going to end. So we know that the elastic section modulus is given by how much? I by Y. So that is I by Y. You can do, you know this thing, the moment of inertia about critical sections. Okay, you know this thing, like for this one was your Z1, the plastic moment from the plastic neutral axis. If we have a rectangular section, if we have a rectangular section, the center we will have what? The center, if I take this line here, this is your neutral axis here. So from the plastic neutral axis, equal area ratio, okay, this is your equal area ratio from the plastic neutral axis. This is a neutral axis. So this is such that your sector, suppose if you are taking rectangular section, this should be divided, it have a equal area ratio. This axis should divide this section into a equal area. Okay, and this Z2, you know, I by Y, which is the moment of inertia about the critical centroidal axis, sorry, about the centroidal axis, your I by Y, this I by Y is your moment of inertia about centroidal axis. Okay. Okay, now I think the meeting, this class is going to end. What is the time now? Time is 11:34. I think then we'll start with our we'll start with the next meeting. I have a class with you, I think from, oh, it was from 11:15. Okay, we will join in that same link. Okay, 11:15 one. From 11:15 I had a class, so that link we are going to join through that link, and we'll discuss a small only the rectangular and the circular part of this analysis there, and then we'll start with our DOS 2 there on the next meeting. Okay, which is from 11:15 one. That link you join. Okay, I'll take the attendance on that class only after this when this gets ended. Okay, okay, Tashi. So we'll take with the examples here. So where is my Cisco? If you want, then you can take all this as screenshot also. Okay, because I don't have these things. I'm just simply typing here. I don't have these things. You just can take a click, take screenshot or photo, whatever you want to do. Because I'll not be able to give you the notes, I guess, for this. I am audible clearly, na? Or my voice is low. Okay. Okay. Somebody was telling like it was low. What was that? Kaputara. Maybe your voice is very low, can't hear anything. Now is it okay, Kaputara? Is there or not? Oh, no. Kaputara. Okay, yes, ma'am. Okay. Push time. Okay, I said, shall I stop sharing my screen now? Because I think it is going to end also, and then we'll join in that next 11:51 meeting. Okay, stop sharing. Okay, you can leave and then you join in that. Oh wait, because this video, which this is recording now, so it will take time for take a break of 5 minutes. Yes, okay, for 5 minutes, and then we'll join in that meeting. So that I'll give. We have to give time for the recording to get converted. This file. Take a break of 5 minutes. Okay.